Now we are going to talk about LC circuits. So these are circuits that contain an inductor and a capacitor connected in series, at least in this case. In these circuits, there may or may not be a resistor. And of course, there may or may not be an EMF device sometimes. But of course, the essential elements are the inductor and the capacitor. So we are going to see how the circuit behaves in the presence of only these two circuit devices. So at the end, of course, I'm going to tell you what happens if there's a resistor on the circuit. So let's quickly go ahead and see what the problem is. So we are going to look at this problem specifically. In the meantime, of course, we are going to understand the behavior. So the capacitor is initially charged with some certain charge, Q0, and the positive and the negative plates are connected with a wire, and that wire contains an inductor. So initially the switch is open, but it is closed at time t equals 0. And we would like to see what happens at time t. Basically, what's the current in the circuit and what's the charge on the place of the capacitor at time t. Of course, to be able to answer that question, we have to write down the circuit equation. So we are going to find a differential equation in there, solve that equation, and then by just looking at this mathematical solution, we can then answer these two questions correctly. But this is the mathematical solution. I'm going to do this in a separate video, but in this video, I'm just going to describe what happens qualitatively. So that's also as important as the mathematical solution. So what is important in here is that there is no resistor on that circuit. So just keep in mind that the resistor is the element that converts the energy into heat. So it basically represents dissipation. So let me just write it down in here. Resistance essentially means dissipation. The dissipation is the irreversible conversion of energy, usually mechanical energy, but there's this electromagnetic energy as well. Irreversible conversion of energy into heat. But the capacitor and the inductor does not have a function like that. So they store energy. So that means they sometimes take energy from the rest of the circuit elements, but sometimes they give back. So they are just devices that store energy. So therefore, the energy doesn't disappear with these two devices. So therefore, we can actually kind of understand what's going to happen in here if we have just these two elements by just using the conservation of energy argument. So the total energy in here, energy of the capacitor, plus the energy of the inductor should remain constant. That's the conservation of energy statement. And in that case, we can see what happens. So one of the important things to keep in mind is that, well, there's an initial energy on the capacitor, of course. So that energy is going to remain in the circuit. So at later times, of course, this energy will be shared between these two devices. So one of the things that you can understand is that there cannot be no static solution. There cannot be any static state where the amount of the energy on these devices does not change anymore. Because, I mean, let's just think of it like that. I mean, let's just consider the initial state, for example, where the capacitor has a charge. The place of the capacitor is charged. So in that case, of course, we know that these two plates are connected with a wire. And we know that the charge is going to flow from high potential to low potential. So that means there will be a current then, since they are connected. So as long as there's a charge in here, you cannot prevent the current. So therefore, whenever the capacitor is charged, the capacitor or the amount of the charge of the capacitor is not going to stay in that situation. So therefore, it's going to change dynamically. Similarly, if there's an energy on the inductor, which means that there's a current flowing. Well, we know that the inductor prevents the sudden changes of the current, so that means that this current is going to continue for a while. And while this happens, of course, we know that this current is going to feed charges to the plates, and so therefore the amount of the charge on the plates is going to change in any case. So therefore, as long as there is an energy on one of these devices or both of them, we cannot have a static situation. So therefore, this energy is going to be transferred from one device to the other. And as a result, you can kind of guess that this is going to have a periodic behavior. So therefore, the energy essentially first passes from the capacitor to the inductor and then back to the capacitor again and back to the inductor again and so on. This continues indefinitely. As long as there's no resistance, this is what we should expect. All right, that's essentially what I'm going to describe in here. But this time I'm going to describe it in terms of basic circuit ideas. So I want to show in here the steps of what happens. So this is our initial configuration. I wrote the time in here at t equals 0, that's the situation. So in that situation we have plus Q0 on one of the plates and therefore minus Q0 on the other plate, right? Just keep this in mind. So the capacitor is actually charge neutral, so that means whatever charge is on one of the plates, an exactly equal and opposite amount of charge should be present on the other plate, right? Just keep this in mind. But I don't want my picture to be crowded, so as a result I just erase this detail in here. So in any case, this is a situation where there's no current on the circuit, so therefore all the energy is on the capacitor, no energy on the inductor. That means that all the energy is the electric potential energy, and there is no magnetic potential energy in here. In any case, so we know that, of course, this is a situation where the plates of the capacitor is connected with a wire, and that wire happens to contain an inductor in any case. So therefore, there will be a discharge. The function of the inductor in here is that it just prevents the sudden changes of the current. So therefore, we know that current is going to rise, but it's going to rise slowly. So as a result, we are going to have at a later time have a situation where we have a positive current flowing in that direction on the inductor, and we will have less charge on the plates of the capacitor, right? So at a slightly later time, we are going to have this kind of a situation. So as I have said before, as long as there is charge on the capacitor plates, this is going to continue. And this is going to continue, and the current is going to basically increase, because somehow we know that this charge is going to basically flow from high potential to the low potential, so therefore it's going to increase the current. So this is going to continue until, of course, this charge becomes exactly equal to 0. So therefore, there is a moment, there's a time, I'm going to call that time as t1, where this charge becomes exactly equal to 0. So I'm going to show that in that picture. I'm going to show it like that. So in that case, of course, the charge would be 0. So I'm going to write it down like that. But that's a situation where the current would still be flowing. That's basically by conservation of energy, because at this point, the capacitor has no energy, so therefore all the energy should be on the inductor, so therefore there has to be a current flowing on the inductor. So by this analysis, we can also see that this is the current, that's the maximum current, basically, because this is the moment where the inductor has the maximum possible energy, which is the initial energy within the system. So therefore, this corresponds to the maximum amount of the current. So that happens at time t1. So what happens next? So we know that the inductor is there. As we have said, the inductor prevents sudden changes in the current. So therefore, this current is going to continue for a while. It will decrease. It will start decreasing, of course, but it will continue. So while it continues, of course, it's going to start charging up the lower plate in here. So therefore, as a consequence, the upper plate would be negatively charged. So the current still continues. This time it's not the maximum current now. the current still continues, so it starts charging up the lower plate. So therefore, just compare this with this initial configuration. So initially the upper plate was positive. Now it is the lower plate which is positive. So the charges actually start changing place on the place. So let's say that so this is not at time t2, so just disregard this. But eventually, of course, this is going to continue until the current becomes zero. So there is a point in time, and I call that time as t equals t2, where this current becomes exactly equal to zero. So current is equal to zero, in which case you can guess that the amount of the charge on the capacitor on the lower plate is now plus Q0. Because, again, by conservation of energy, because at this configuration, the amount of the energy on the capacitor is the same as the initial energy in there. But in any case, this is exactly like the initial configuration, except that the charges have changed their places. So therefore, let me draw these arrows. So from t equals t1, then we pass to that stage. And from t equals t2, we will pass to that stage in here, where the place will start discharging again, but in the opposite direction. So therefore, the amount of the charge on the positive plate will decrease. There will be a positive current along this direction. And the amount of the negative charge in here will also decrease in magnitude. So as a result, this is essentially, again, same as this kind of a situation, except that the directions have changed. So again, this will continue until the charge becomes zero. So let's say that this happens at t equals t3. When the charge becomes zero, so let me also erase this. So this is a situation where the charge on the plates is again zero once more. So the charge on the upper plate, lower plate, doesn't matter. It's equal to zero, at which point, of course, the amount of the current on the inductor would be again maximum in magnitude. It's maximum and positive along the given direction, of course, but just keep in mind that compared to the situation at time t equals t1, the direction is reversed now. And then, of course, after that, it will start charging the upper plate in here. So as a result, I'm going to cut the story short. So as a result, we are going to have a situation in here at some later time. So I'm going to call that time as t equals t4. So at time t4, let me write it in here, comma t4, we are going to reach to a situation which is exactly like the initial situation. So as a result, this is a periodic thing. So therefore, the period is t4. So after that, everything is going to start again. So therefore, at time t4 plus t1, we are going to have this situation again. Let me erase all of these. At time t4 plus t2, we are going to have this situation, and so on. And so therefore, at time 2t4, we will be back with the starting configuration, and so on. So it will just continue like that. Right? So as a result, by using this, we can actually plot the amount of the charge and the amount of the current. So I have just drawn these things in here. So these are the times corresponding to the individual steps that I have shown earlier. So the period is equal to t4. And so if I draw this with a yellow color like that, with a thick yellow line, the amount of the charge in here is going to have this kind of a behavior. So initially it's maximum Q0. At time t1 it becomes 0. At time t2 it becomes this time maximum in the negative direction in a way. So it's become, as a quantity, it becomes a minimum. At time t3 it becomes 0 again, and then we have this. So let me write down the values in here. So we have plus Q0 and minus Q0. Since I have to use the same graph, I need to define the charge unambiguously in here. So therefore, in I don't know, in this kind of a picture, for example, we might define Q as consistently as the amount of the charge on the upper plate. So therefore, at time t equals T2, the amount of the charge on the upper plate would be minus Q0 then. So as a result, this is what we have in here. So as a result, this is a periodic change. So at this time, so let me redraw this. At this time, we are going to reach to the initial configuration, and then this is going to continue repeatedly. So this is a periodic change. Since the energy still remains there, we are going to have this kind of a situation. It's the same for the current. This time the current starts from 0. It reaches a maximum at some point, and then becomes 0 again, and so on. So this also repeats periodically. What are the current values? So I just call this as I max, but by the conservation of energy requirement, we can easily compute these. So the minimum current is minus I max, and the maximum is I max. So what about the energy? So that's not the charge in here, but let's say that I'm using a blue color for the energy of the capacitor. So let me write it down like that. Energy on the capacitor. So I'm going to also use a thick line for that. So capacitor has the maximum energy at the initial time. At T1, the capacitor becomes completely discharged, so therefore its energy becomes 0. The energy can never be negative, because if you remember, the expression of the capacitor's energy is always a quadratic function of the charge. So therefore it's either 0 or positive. It can never be negative. So therefore, at half of the period, it's going to become maximum again. And in here it becomes 0, and then at full period again it returns back to the original energy. But of course the energy in here has a period which is basically half of the period in there. All right. So as a result, we are going to have this kind of a graph for the energy of the capacitor. So I'm also going to draw the energy of the inductor with a red color. I'm also going to use a thick color for that. So in that case, inductor starts with 0 energy. Initially, there is no current. At this point where we have the quarter of the period, the inductor's energy becomes maximum, where the current is maximum. And then, of course, it becomes 0 again, and so on. So therefore, if one of them is maximum, then the other one is a minimum, and so on. So we have a graph like that. And finally, if I use, I don't know, the yellow color for the total energy, so let's just say it like this: U tot is the energy of the capacitor plus the energy of the inductor. Again, I'm going to draw a thick color for this. So that's basically a constant. So therefore, this is going to be a line constant. Right, at this point, I'm going to have a analogy. Let me add one more thing. So what happens if there's a resistor? If there's a resistor in the circuit, so as a result, we have a circuit like that. But the setting of the circuit is going to be the same, except that there's an additional resistor in here. So as a result, we have this kind of a thing. So it's basically obvious. In that case, the resistor is going to convert some of this electromagnetic energy into heat. The power of it doing so depends on the amount of the current as well. But in any case, that doesn't change the qualitative picture. So in that case, of course, for example, for charge, instead of a periodic change now, we are going to have a decaying periodic change in here. So once we solve the mathematical equations, we actually see that this is an exponential decay. So therefore, in principle, it continues indefinitely, but there's always some certain typical lifetime in here where for all practical purposes, you say that the oscillation continues, and after that, you just neglect the oscillations. In any case, so that's the last thing. There's a mechanical analog of this this motion. So that's basically the vibrational motion of a spring. So just consider, for example, a mass attached to a spring. I'm going to assume that no friction. That basically corresponds to no resistance assumption. So friction is also is a dissipative effect. So it just converts the mechanical energy into heat energy. If there's no friction, then therefore this doesn't happen. So in that case, the total energy is basically the kinetic energy. Let me write it down like that. Plus the potential energy. This has to be a constant. So the kinetic energy is 1/2 of mv squared, and the potential energy is 1/2 of x squared. This is more or less like the situation in here where our total energy is energy of the capacitor plus energy of the inductor. Energy of the capacitor is q squared over 2c, and the energy of the inductor is 1/2 of L times I squared. So in each case, energy depends, each energy term depends on the square of a variable multiplied with a constant, and in each case, of course, we have these 1/2 factors in front, but in any case, so for the case of mechanical problem, kinetic energy is proportional to v squared, and potential energy is proportional to x squared. So we just start with this kind of a situation, for example, where I compress the spring and then release from there. So initially, velocity is 0, but there's displacement. So that means initially there's potential energy, no kinetic energy. Then we know that at this situation it cannot stay because it's going to accelerate towards right. So eventually, of course, we know that it's going to pass from the equilibrium position. So while it is passing from the equilibrium position, in that case, the displacement is 0, so the potential energy is 0. So at that point, the speed is maximum. So that's the point where all the energy is converted into kinetic energy. Then at a later time, all the energy is converted back into potential energy, where the kinetic energy becomes 0 again. And then there's a point where, again, we have the potential energy is 0, kinetic energy is maximum. And then finally, we go back to our initial situation. So after one period, we are back with the initial thing. So there is actually quite a similarity between the LC oscillations and the mechanical oscillations like this one. So this is actually a very nice analogy because actually the mechanical oscillations are something that we actually see a lot in nature. So we see them in molecular vibrations, for example. So it's actually a nice example, nice thing to know that there are also these oscillations that does not have any mechanical analog. So these are nice LC oscillations in here that I have mentioned. So they're actually kind of charge carriers which are moving around in here, but that's it's a very microscopic point of view. So if you just look at it from this point of view, the energies formed from the potential energy of the electric field that's produced in between the place of the capacitor and the magnetic field, potential energy of the magnetic field produced inside this solenoid in here. Right? So therefore, in that case, there are no kinetic energies, actually. There's no macroscopic object which is moving. So in a way, there are these two different potential energies, but these are electromagnetic energies. So we have a situation that an oscillation that results from the exchange of the energy between these two forms. So essentially, this is the whole explanation for the oscillation. So we can also derive this behavior mathematically as well, which is what we are going to do next.